Hello, everybody. Welcome back to DeepRob for Lecture 12. Today's lecture is on object detection, and we can get started, I think. So maybe I'll fix this. So a couple, I guess just one administrative update, which is about Project 3. So it was officially released last night. Got the code all finished. So the instructions are up on the website, as well as starter code. And then also, exciting about this project is we're sort of graduating from classification to detection, at least midway through the project. So we have a new data set, the props detection data set, which will have, I think there's, like an animation here. So this will have, it's like 2,500 training images, 2,500 validation images that are still of our, these are actually like officially called YCB object. They're objects from the YCB object model set, or object and model set. And these images were collected in our lab upstairs, as well as the labeling was done upstairs. So, so detection is what we're going to be talking about today. So you'll get more of exposure to what detection really is and how you'll implement some of the algorithms. But we have this new data set, which is exciting. And it'll be due exactly 2 weeks from when it was released. So you have until Tuesday, February 28th. At midnight to do this project, and yeah, so I think that's the only administrative update today. Are there any administrative questions I can answer before we get into object detection? Okay, cool. So, all right, so just as a brief recap, last lecture you'll remember we were talking about PyTorch and TensorFlow as deep learning software frameworks that we can use to start actually implementing our convolutional neural networks and our other deep neural networks. And so up to this point now, we're really set to actually, not only set up our architectures and start training them, but implement them, evaluate them all in software, and sort of get off to a good start there. But what we're going to start looking at now for the rest of the course are these kind of like more approaches, more techniques, more application areas where we could actually use our neural networks for actual problems within robot perception. And so today's lecture is going to be starting us off in that direction. Because up to this point, really what we've been looking at, it has been restricted to image classification. So we've had this problem set up where we're going to say like our robot takes in some color image of a scene. We pass that through some feed-forward, maybe convolutional neural network like AlexNet. We get out some feature vector, and then we classify that feature vector according to some discrete set of class labels that we're looking for to try and understand what is in that image. But really, what we can do with our images or our other sensors on our robot doesn't stop there. So a set of classical computer vision tasks are laid out on this chart, and some of them are what we're going to be talking about in this lecture and in upcoming lectures. So semantic segmentation would try to say, like, let's say that we collect that image of our scene, but now what we want to do is not just label just overall what's in the image itself, but at every single pixel, try to predict what information can I sort of say about every single pixel. So that semantic information then is what we mean by labeling every single pixel. And then segmentation is this notion that by labeling every single pixel in the image, you'll start to sort of define regions that are similar in what is within each region. And so that's taken together then semantic segmentation. In today's lecture, what we're going to talk about then is a little bit more of a coarse, maybe description of what's in an image, but that's called object detection. So this is where we're trying to localize some bounding box, so some region of the image that would contain a specific object of interest. And then what we want to do is detect within an image all of the objects of interest and localize all of them within the pixel coordinate space of that image. A little bit different then would be sort of maybe kind of like combining semantic segmentation and object detection, or maybe you would want to localize every single object of interest within the image space, but also label it not at a bounding box fidelity, but actually down to the pixel level fidelity. So you'd end up with a segmentation mask is what it's called, which is essentially like a region, a bounding region of pixels that would contain every single object of interest in the scene. So like on the far right, for example, like in this instance segmentation, we're trying to segment all these different types of chocolate-covered pretzels, which then maybe we could like extract just those pixel features for some downstream task like a pose estimator that would be specialized to just take as input the segmentation masks. So these are a collection of vision tasks which are really going to be the focus of our lectures this week. So in today's lecture, we're going to be talking about object detection. But before we do that, I wanted to cover briefly one note which we had left out of a few lectures ago, which is this concept of transfer learning, because this connects image classification to these other downstream vision tasks that are very common for our robots to have implemented on them. So what is transfer learning? Well, transfer learning ultimately, it's very pervasive. So I kind of guarantee you that if you've worked with a pre-trained neural network, then you've been either using or implementing yourself transfer learning. So you see this very, very commonly. And what it ultimately is trying to do is generalize one neural network that was trained in one task to some new task or some new data set that the network wasn't trained for. And so let's look at how that works. So the idea here is, let's say that, let's say Facebook has published some PyTorch pre-trained model, which we had talked about in the Torch Vision package during last lecture. And we might want to use this pre-trained model that was trained on ImageNet because maybe we can't afford to train a model on ImageNet. Maybe we don't have enough compute. So what we could do is we could download that pre-trained model from ImageNet, which is just performing classification. We could take what we would call the backbone, which is sort of like all of the layers up to the very final like linear classification layer, and we could just extract just those layers from this network, and we could call that then a feature extractor. So if we were to feed in some new image to this network that we've extracted, the final output isn't going to be a classification decision, but it's going to be some embedding in some learned feature space of what features the network thinks this image contains. And so hopefully that embedded space that's been learned could be useful for maybe some downstream task, which we might be interested in, which is not necessarily classification on ImageNet. And so what we can do is we could try freezing, so basically like not training all of these layers that we extracted from this pre-trained network, but then add in one additional final classification layer, like a linear layer at the very top, which is randomly initialized, and then just train that one classification layer or that one, let's say, detection layer at the very end on some new task using these pre-trained feature extractors. And hopefully that would perform well and sort of reduce how much training we would have to perform. And so it turns out that in practice, on a lot of tasks, this is actually the case, that using this sort of pre-training approach, where you take some backbone network that's been pre-trained on ImageNet, and then you try to fine-tune some like final portion of like a classification head on top of this feature extractor, works out very well in practice. So these results are from one of the early papers that found this in practice. So what they are comparing here are, so like the blue and the green lines are showing if you took a pre-trained model on ImageNet and then you trained just an SVM on the feature extractor portion of that pre-trained ImageNet model, but applying it to a new data set, so this Caltech 101 data set, just the point being that it's like a different distribution of data, that the resulting accuracy for these models was outperforming a pre-existing fine-tuned model that was just fine-tuned on this one data set. So the takeaway here was kind of shocking, right? Which was that like these learned features from these deep neural networks from ImageNet actually were transferring to new data sets, even with a fairly rudimentary like final SVM layer for classification, over models that were specifically trained, like kind of specifically handcrafted and engineered for this Caltech 101 data set. So this sort of started some excitement in that direction, and it's just continued. So I would say, so here's like another result showing like that this kind of same result carries across different data sets. So in this case, it's like bird classification. So it's like a different variant of data sets from this like Caltech 101 overall data set. And so again, so like the main takeaway here was that it's sort of surprising that image classification might be sort of like a good pre-training task that then can carry over to other data sets or other tasks. But this is kept on. So like these results have carried over into classification for, you can see here like specific objects or scenes or birds that are not necessarily from the ImageNet data set. And it hasn't stopped there. So like I was saying, pre-training is essentially, I would say like always the default. Like if you're gonna try coming up with some new pose estimation model, it's pretty rare that you would want to just train it from random initialization. You might want to sort of start with some backbone feature extractor that's been trained on ImageNet just because it'll speed up your training generally. So how would that work for like speeding up your training if you were trying to apply this backbone, like we're saying, that's been extracted from a classification network to maybe a pose estimator model? So what you can do is you can take your pre-trained model from ImageNet, you can extract this, like all of the features up to the final classification, let's say layer, and then what you do is kind of like I guess I described earlier. So you could just then randomly initialize some new final classification layer where all of these preceding layers have been initialized from this pre-trained ImageNet model, and then you're going to continue training through this entire network. So hopefully you're sort of fine-tuning these learned features from some very useful, very informative initialization that was trained on ImageNet, but you're sort of fine-tuning them and sort of specializing them to whatever data set you're going to now train this model on or fine-tune this model on. So to do this, like in practice, a few kind of tricks to be aware of. So typically what people will do if they're going to try and fine-tune a model that's been pre-trained on some other data set is they'll actually, during like the initial training steps for fine-tuning, they'll freeze all of the network weights that they used in their sort of backbone or their feature extractor, just for the first sort of few steps, and that's kind of a hyperparameter, how many steps. The reason why is that on those initial steps, the gradient coming through this randomly initialized final layer that you've created can kind of destroy all of the informative features that were learned by the feature extractor on ImageNet. So the thinking goes, okay, like if we freeze this backbone or this feature extractor for a few steps, then hopefully this new layer that we've initialized can sort of get reasonable, can sort of learn itself to be like a useful classifier in relation to this backbone, so that then when we start training this entire backbone, the gradient is actually informative for the backbone, and it doesn't just like, you don't just have like huge gradients for these initial weights at the first step and you kind of destroy all of your useful pre-training. So that's one useful trick. Another one is usually you'll reduce the learning rate during fine-tuning than whatever was used for training the backbone on ImageNet. So maybe like reducing the learning rate by an order of magnitude is a common trick. But again, I'll point out like all of these are hyperparameters, right? So you're sort of increasing your hyperparameter search space by doing this fine-tuning. And let's see, sometimes also, yeah, so another trick is sometimes like these very early feature, like these very early features that are learned from one of these backbones will be like those edges and those color gradients. And so sometimes a trick will be to just not even fine tune those at all, just leave those early ones frozen, because you'll save computation because the backprop can actually be pretty expensive through those if they have a large number of channels as output. And hopefully you're not losing too much because like edge detection or color gradient detection should hopefully be useful carrying over across at least vision data sets. Yeah, so those are just some tricks there. So compared with, yeah, so the downside with fine tuning over just taking a feature extractor and just leaving it frozen and just training like a final classifier on that is that fine tuning is going to require generally some more data to actually train like a linear model instead of some simpler linear classifier like the SVM. It's more computationally expensive because you're going to now be backpropagating through this entire network instead of just maybe your final layer. But the advantage is you can specialize a little bit more to your data set, so you could result in general in higher accuracies. So one useful thing, or like one reason why this has been of interest to the vision community and the robotics community, is that it's sort of been found that image classification turns out to be a really good pre-training task. So having a better model on image classification results actually in better downstream models for pose estimation or semantic segmentation or object detection, because by taking that pre-trained ImageNet model or pre-trained image classification model and using it on those downstream tasks, at least what's been observed is you get better performance on those downstream tasks. And so it's kind of incentivized a lot of this development that we've seen and this specialization on image classification models. So like this ImageNet challenge, for example, like all the excitement and interest in it is not only because people are interested in image classification, but it's because a lot of researchers and a lot of people in practice will take the models from the image classification community and then transfer them to their own tasks, which creates a lot of citations and just like a lot of interest in what's happening with image classification. Question? the questioner was pointing out that on this model, when it was pre-trained on ImageNet, ImageNet has 1,000 classes. So the final number of output scores from this fully connected layer is 1,000. But for fine tuning, when we go and remove that and add some new layer, we could have an arbitrary number of maybe classification scores that we want this to produce. It could be 10, it could be 10,000. And then the kind of question is like, is it really the case that the features that were extracted from this feature extractor are useful on these maybe way fewer number of classes or even more, like larger number of classes? And the answer actually is yes. So it ends up that these features end up being useful. Even in the case where none of the classes on your data set were in ImageNet, it's still useful. And to some extent, this can make sense because the classes in ImageNet are very broad. So it's learning, like especially at these higher levels of features. I would point you, for example, on some of this, if you're interested in like some of those Distill blog/article posts that I've been linking on the website that go into like interpreting the features that are learned. On like classification models that are learned on ImageNet, these high-level features that are learned are actually detecting like patterns and textures that are kind of agnostic to a specific class. So it'll detect like fur that's agnostic to a specific animal from ImageNet. So then you can imagine how if you have some new class, some new animal maybe in a data set that you're trying to classify, having that detection of fur in one of these intermediate features can actually carry over and still be useful, even though this new class that you're trying to fine tune on was never even represented potentially in ImageNet. That's right. And I would even say that like it can even be the case that if you take like even transferring even to data sets that are very, very different, like if you take a data set like from space imagery and try and take ImageNet, which has like natural classes and you're trying to apply it to that, the transfer learning can even be useful there, which is fascinating. But I will point out, generally, like transfer learning works better the closer your fine-tuning distribution of data is to your pre-training distribution. Yeah, thanks for the questions. Other questions I can answer on this fine-tuning or why it's useful? Okay. So like another takeaway, right? So from this notion that having a classification model be useful for downstream tasks. So these results here are actually proving that out or illustrating that. So looking at object detection as a downstream task that would use these transfers of learned features from classification, what's being shown here is the object detection performance, we'll say, as the y-axis, and then different detection algorithms that use either the same or different backbones from image classification. So for example, FastRCNN is one specific type of object detection algorithm, and what then these two bars are showing is that if you take the FastRCNN detection algorithm and you just substitute the backbone, so like the image classifier backbone that's used within the detection algorithm from AlexNet to the more to like the better performing VGG16, you see a corresponding increase in detection performance for the same detection algorithm. So it's controlling for everything else except for this classification backbone that was pre-trained. And we see the same general trend even if you change the detection algorithm. So moving like to faster RCNN, if you substitute ResNet 101 for ResNext 152, which is a more recent, more advanced image classification model, which also has better performance than ResNet 101 on ImageNet classification, we see again like an increase in detection performance. So like these results are again motivating this idea that having a better image classification model can be useful for downstream tasks. Yeah. I don't think I have like a sort of one-size-fits-all answer to that. So the question was, how can it be that features learned on classification, which are so geared in some sense towards one score for one class as output, versus features that you'd think you'd need for detection, where you're going to have maybe multiple bounding boxes in an image, and every bounding box is itself now like a pixel coordinate. How can it be that that those features are useful across those two tasks? I would say I'm not sure I have like a great answer on that. That's one of the interesting kind of results here. I think I can point you to some papers probably like if you come up and talk to me after, I can look at some papers that try to like do some ablation studies on that, but I'm not sure that there's like a concrete answer on why it's so useful, but it's fascinating. I see. Okay, yeah. So more on the practical. So for object detection specifically, so we'll like the focus of today's lecture will be on RCNN, and then on Thursday we'll talk about like fast RCNN, faster RCNN, and mask RCNN. So we'll get into the details of how the detection algorithm works. But to answer your question, you can imagine as long as you have some algorithm that can use the feature extractor. So right, so like that feature extractor might give you an output like for some image input that's like say 224 height by 224 width by 3 channels of input for RGB. The output from that feature extractor, let's just hypothetically say, is 10 pixels by 10 pixels by 256 channels. As long as the detectors use that output in some way, then that's how it can transfer. So you can have like some specialized algorithm on top of those learned features, maybe which we'll look at today. But that's what we mean by transferring it. So even if you don't just have a classification head as your final like connection from the feature extraction to your detection, as long as you're using those learned features, we'll still call it transfer learning. Yeah. Okay. So let's see. So transfer learning. Yeah. So sometimes what you'll find, or what's been found, is that if you don't use transfer learning, but you instead just use random initialization and train for even longer, you can achieve the same final performance in terms of accuracy as if you had used transfer learning. But again, this motivates like for the practical use cases, you'd usually probably want to start with transfer learning just because it'll speed up your training as opposed to random initialization with a lot more training. Also, I want to point out that this is a very active area of research. So even at this year's ICRA coming up, there's a workshop entirely dedicated to pre-training for robots. So they're trying, so like the motivation here is trying to like look at what's been happening recently, like with ChatGPT and a lot of like the vision transformers, which use pre-training very heavily and to great effect. Trying to carry that over into robotics is an open question of how we can actually do that effectively. So I'll also point out that their call for papers has a submission deadline of April 14th, which would fit really well with the course. So if you're working on a project that uses pre-training, this could be interesting to look at for maybe submitting to. Okay. So with that background on transferring classification to new tasks, let's talk in a little bit more detail about at least one of these tasks that we might want to transfer to, which is object detection. And so that's going to be the focus of today's lecture. So how do we define object detection? So the basic setup is we're going to be given as input just one RGB image, so one color image, and what we want as output is a set of detections for the objects of interest in the image. So for every single object of interest that we find within the image, we want to produce some category label. So this can like a discrete, basically, classification for this specific object that's been detected. And that can be from a fixed, predefined set of labels. So that's the same as kind of classification as we've been looking at it. But in addition, what we want is the actual location within the image for this detected object. So we want a bounding box, which is going to be 4 numbers. It'll be like essentially defining like the center location of the object as well as the width and the height of this bounding box, which contains all the pixel features corresponding to this object within the image. And so if we get all of those detections correctly, then we'll be able to localize every single object of interest, at least spatially within the pixel region of the image. And so what's probably becoming apparent as we start to think about this, or how it is we would actually implement this with the neural networks that we've been looking at so far, is there's a number of challenges to actually go about implementing this. So the first challenge is this network, if we were going to try and implement this as a network, would have to have multiple outputs, right? So as was kind of pointed out by that question, you could no longer just have maybe a final linear layer that will produce a set of scores, because we don't know how many objects we're going to detect in a given image, right? In one image, there might be 1 object. In a second image, there might be 3 objects, like here. In another image, maybe there's no objects that are detected. So it's like this variable-sized output that we're going to have to overcome. That's one thing. Another is now we have 2 actually like semantically distinct types of output that we want our network to produce. On one hand, we want it to produce labels, like discrete category labels, and on another hand, we want it to actually produce these bounding boxes, like this localization information. And so that's another challenge we're gonna have to do, to sort of deal with. A third then is that now we're gonna be working with, like in order to have high fidelity detection, so that means like detection at a very like, kind of like arbitrary ranges of resolution, from maybe objects that take up the full image to objects that take up maybe a small portion of the image, we're gonna wanna feed in very large images to this detector so that we can identify objects at multiple scales of resolution. So now we're gonna have also to deal with large images that are coming into our network. So we're gonna have maybe memory constraints that we're gonna come up with, just computational bottlenecks in general. And so that we're gonna have to also try and handle. So all of this is gonna be the role of an object detector though. Okay, so let's now think, if we're gonna try and implement this, how we can start to go about defining these different labels that we wanna produce as output. So the category label we're pretty familiar with from image classification. So let's instead focus now our discussion on bounding boxes and how we can define these. So typically in object detection, we define bounding boxes in a format which is called axis-aligned bounding boxes. So what that means is you'll define the coordinates of the bounding box as essentially like the four corners of this bounding box, and then you would imagine following the axes of the image, like the x and the y coordinate, you would connect those coordinates kind of correspondingly. This is in contrast to an oriented bounding box, where you would define the bounding box to actually have some rotation that would actually like allow the axes of the bounding box to not be aligned with the axes of the image. This is generally, like these axes aligned, or these oriented bounding boxes are usually much less common in object detection literature and in object detectors. The reason for that is probably because oriented bounding boxes are harder to label. So it's harder to come up with data sets for oriented bounding boxes. Just because you can kind of imagine, if you're a human labeler, it's easy to kind of like click an initial corner and then drag a box that's the right width and the right height for an axis aligned box. But if you imagine trying to orient a box, like every time you change the rotation, you might have to realign the actual corners to sort of make it fit. So that's probably why axis-aligned bounding boxes are more commonly seen. Just it's easier to make data sets for them. Having said that, one of the interesting kind of phenomenon that come about by using axis-aligned bounding boxes is that you can see, for example, for these like thin objects that are rotated in a non-axis aligned fashion, a huge number of the image features or the pixel features that are within that bounding box are now not actually related to the object of interest, right? So like in the case of this fork where my cursor is, most of the pixels in this bounding box are not on the fork. They're on other objects in the scene. So that's kind of an interesting result of our choice of labels as axis-aligned bounding boxes. So that's something that our object detector may have to overcome, potentially, is that source of like sort of additional noise or sort of like maybe not very informative features. Okay, so another distinction in how we describe bounding boxes is this notion of what we could call modal versus amodal boxes. So in most object detection data sets, the bounding box will be defined for a specific object of interest as covering only the visible portion of the object. So in this image, for example, like this blue box that we have drawn is what you would typically see in a data set if it was going to be labeling this Flips white chocolate covered pretzel bag in the back. So the bounding box is only covering the portion of the object that's visible. This is in contrast to what would maybe be called an amodal detection data set, which would cover the region of the image corresponding to the entire object, even the portions that are occluded. So this green box, for example, is trying to show, like if you imagine how large this pretzel bag is as it's covered up by the Doritos bag, it would actually be larger than the blue box. So one word, I mean, you don't see this used, I would say, too often, but this typical use of bounding boxes you could call modal detection in contrast to this amodal notion of detection. I will point out that our data set, this props detection data set, is actually an amodal detection data set. And so that's something to be aware of. But for our case, there's not that many objects that are occluded, so I think it's kind of an interesting source of noise that I actually want to look at for this project. Yeah, so this is amodal versus modal object detection. Okay, so how now, like let's say that we have, oh, question? Yeah. All the major ones that I can think about are modal. It's like Cocoa. Yeah, I think they're pretty much all modal. Yeah, and a lot of the times, so you can, like a lot, that kind of also gets to like how it is you label data sets. In the case where you have, like in the cases where maybe where you're like estimating the pose of an object, there's where you can actually label amodal detection, because if you know where the object is in 3D space, then you can project essentially the object into pixel coordinates regardless of what occlusions there are. But in the case where you don't have that 3D information, where you're just trying to annotate data on pixel level, it's really hard to estimate how much of an object is occluded just by looking at the image. Yeah. Let's see. Other questions I can answer on? Oh, let's see. There was a question on the chat, which I maybe have passed over by now, but the question was, what is FPN standing for? Let's see. I think I've gone past that by quite a bit, but I think if that's in relation to the RCNN detectors, which we'll talk about, it'll be a feature pyramid network. But I can try and answer that after too, if you can remember which slide it is on. Okay, so let's say now that we're using access line bounding boxes, and let's say that we're working with modal detection. The next question that we should start to think about is, like for the purposes of starting to maybe think about like setting up a loss function, or just trying to get an understanding of like how our predicted bounding boxes are at least comparing to our ground truth bounding boxes, we should try to think, how can we compare two access line bounding boxes that have been predicted? So what we can do is we can use this measurement called intersection over union to actually compare two bounding boxes. So let's say that we have this setup here where we have some ground truth bounding box coming from our labeled data set over the object, and then we have some prediction, and we want some scalar measure of how well our prediction aligns with our ground truth bounding box. So what we can do, and kind of as the name suggests, we can measure how many pixels there are in the intersection between these two bounding boxes, and we can put that into the numerator of our equation. So we'll just measure what's the area of intersection. And then in the denominator, we'll take the union of these two bounding boxes. So all of the pixels that are contained in either one of the two bounding boxes, and use that within our denominator. And that'll result then in a scalar value measuring how sort of good or how much overlap there is between our two bounding boxes. So as a general rule of thumb, having an IOU that's greater than 0.5 would be sort of like a decent prediction. It's certainly not perfect, but it's at least covering the object. Having an IOU that's greater than 0.7 it would be considered pretty good, visually, kind of qualitatively, like a pretty good detection. And then anything that's over 0.9 would be considered like an almost perfect detection. I'll also point out that sometimes, like viewing bounding boxes and then like thinking about the IOU, like sometimes it can be a little bit deceptive, especially as you start to move further away from the like almost perfect detections. So having like a nice measure, like a nice scalar measure, is useful. Okay, so let's say now that we have this measure for how it is we can compare bounding boxes between our predicted boxes and our ground truth boxes. Let's now think about how it is we could go about setting up a detector for just a single object. So this can be thought of as like our basic, like initial attempt at an object detector. So let's try and reuse as many of the concepts as we've looked at up to this point. So let's say that we have some image. Let's say we pass it through AlexNet. So we pass it through some convolutional neural network, and we get out a feature vector. So in this case, let's say we have a feature vector that's of length 4,096. So thinking that because we're just going to be detecting, like, let's say a single object in this image, we know that we want to predict a class score and also then a bounding box for the single object. So how could we go about doing that? Well, the first thing we could do is we could take our feature vector and pass it through a linear layer to predict out a set of class scores for each of the classes within our objects of interest. And then we could train that using a softmax loss, similar to how we've been doing, right? And we could then compare this predicted set of scores to the single correct label. And that's how we could go about training the sort of like what is in the image. So this is what we've looked at up to this point. What we could imagine doing, though, is appending on to this overall architecture a second branch at the end, which takes our final feature vector, passes it through a separate fully connected layer to produce, as just a regression output, a four-dimensional vector, which is the xy coordinate of the center of the predicted bounding box, and then the width and the height of the predicted bounding box. And then we could imagine, because this is like treated as a regression problem, this bounding box coordinate prediction, we could imagine training this with an L2 loss to try to force the predicted bounding box to be close to the actual ground truth bounding box for the single object in this image. So this first branch we could think about as sort of training the what is in the image, and then this second branch would be trying to train to detect where in the image is an object. The challenge though with this, right, is that in order to actually train this, we need a single scalar loss function to actually apply backpropagation. So what we would probably try doing as like a logical step is to just take these two individual losses, add them together, and then use that as our final loss to train both in tandem, right? So what we could imagine doing is defining some total loss L, which is the sum of our classification loss, as well as our bounding box loss, and then we could train using backprop through that. One additional hyperparameter that we are defining by setting up our loss in this fashion is this lambda here, which is scaling our bounding box loss, our regression loss. The reason that we have this lambda is because you would want to try to essentially like scale these two losses so that they're relatively in proportion to one another, because the actual objective of a softmax is very different from the objective of an L2. So trying to bring these two in some range can actually improve your final performance, because it could be the case just by the way that the loss function is defined, or the way that your bounding boxes are defined, that the L2 loss would like very much dominate the softmax loss. So your gradient descent would sort of be just focusing heavily on the L2 loss and trying to make that portion good, and then ignoring the classification loss. So by having this lambda hyperparameter, you can sort of control how much of an emphasis you want your optimization to pay to each of the two different objectives. So we could try using this as an initial object detector. This would be a reasonable implementation. And so what we could then try doing is like applying transfer learning. So we could even take like an off-the-shelf pre-trained AlexNet and then train our detector using the pre-trained feature extractor, and then just fine-tune these final classification and bounding box heads. The problem with this is that images can have more than one object within them. And so what we would run into is this would be limited, right, to just detecting one object all the time. So we'll at least get a bounding box. So this is an improvement over our classifiers, which would just have the classification head, but it's not going to be able to handle this multiple output scenario. So how might we go about trying to predict multiple bounding boxes for every given image? Because if we think about the types of images that our robots are going to be seeing, it's very commonly the case that they're going to be picking up sensor data that has multiple objects within them, right? So for example, like in this first image, it actually does only have maybe one object of interest. But you can imagine just if the robot sort of backs away, or if the store shelf is arranged just slightly differently, now all of a sudden we need to detect 3 objects and correspondingly have like 12 total numbers to represent the bounding boxes for those 3 objects. Versus even like a more cluttered scene, which is also very realistic and even just taken here in the Eigen Cafe, which again, for these very many objects, you're going to need 4 numbers for each one to represent the bounding boxes. So we're going to somehow have to have our model be adapted in a way that it can output multiple bounding boxes for every single image that it's seeing. So how could we do this? Well, maybe the initial sort of like naive idea that we could try is we can imagine just taking a sliding window approach, where we actually just crop out of the image different sub portions and feed each one through our now single object detector network, and try and detect the class for this sub window in the image, and also a bounding box that's in relation to this sub window for object detection. So in this first case, for example, you can imagine if we take where this red box is as our first sub window, and imagine now feeding that into our detector / bounding box predictor, and hopefully it would produce that this first bounding box here, this first sliding window, has no objects of interest, it's background. And then we could move that sliding window to some different portion of the image. It could even be scaled differently. And now we could ask our model once again, like, what's in this portion of the image to try and classify. Hopefully it gets it correct as the flips pretzel bag. And then keep going, right? So we could keep on sliding our window into different portions, and for every one of those portions, have it try to predict a different bounding box or a different classification. The problem with this, or maybe something to think about with this, is just how many possible sliding windows there are for a given image. And so it turns out that this approach will be extremely expensive in terms of how many feed-forward passes we'll have to do for our network just to produce an output set of detections for one image. So what you can do is you can like run through the math here by saying like, how many possible boxes are there if you have some fixed image that's of size like capital H by capital W for height and width. And then if you consider boxes that are of some set size like little h and little w for height and width, basically you can actually calculate that there's, if you imagine then like a stride of 1 pixel, well, in total, you're going to have a possible set of x positions, so like horizontal positions that you could slide as being like the total width of the image, subtracting then 1 width of one of these bounding boxes just by the fact that you'll sort of like run out of room when you slide kind of to the right, if you kind of visually imagine it. And then you add 1 just as like to correct for like the 0 index. And then you can have the same kind of math for the possible set of y positions. And then if you imagine at every single possible horizontal position of your sliding window, you could also have every possible vertical position of your sliding window. So you'll multiply those two together, and that's going to be the total number of bounding boxes. So if you imagine trying to run a feed-forward pass on this many bounding boxes, it can quickly become totally infeasible. So taking just as an example, like an 800 by 600 sized image, which is not out of the question for the sensors that we have nowadays on robots, that's going to have like 58 million boxes. So that'd be 58 million times that you'd have to pass an image into your AlexNet feature extractor and then your final fully connected layer to produce a bounding box. So that's going to be totally infeasible, right? So instead what's used is what's called a region proposal approach. So the idea here is a lot of those sliding windows are probably useless. So if we had some approach where we could sort of propose the plausible regions early on and just focus our computation on those, then we'll have like a lot more efficiency and hopefully not lose anything in performance. So what we'll do is, or like what's been done in the past is, there's been a set of approaches proposed to do this automatically. So typically these have been heuristic style algorithms. So they'll run maybe like some blob detector algorithm and then try to extract the bounding box coordinates over all of the possible blobs and use all of those bounding boxes as proposed regions. We're not going to focus on too much on how these kind of heuristic-based algorithms have been implemented. It kind of turns out that the general trend for all of machine learning is anytime there's been a heuristic proposed or like some handcrafted approach proposed, the machine learning community tries to then propose learning how to do that heuristic or that hand engineering algorithm from data. And a lot of the times it turns out that that works well or even better. So this is also the case for object detection. So what's been happening recently is that region proposal networks have themselves actually learned how to propose regions that don't use heuristics. But in today's lecture for RCNN, RCNN does use a region proposal approach that was like a heuristic-based algorithm. It uses this selective search algorithm. But we're not going to focus too much on how that works. Let's just assume that we have some black box where we give it an image and it proposes some candidate set of regions as bounding boxes in the image that our algorithm should sort of focus on or pay attention to. And so in the case of RCNN, selective search is constrained to give us maybe, let's say, 2,000 regions. So just note that like 2,000, right, that's, what is it, like at least 3 orders of magnitude or maybe 4 orders of magnitude less than the 58 million that we would be looking at if we did the sliding window approach. So it's a huge reduction in how much computation we're gonna have to do, right? We'll just try to run our final detector on these set of proposed regions as opposed to every possible sliding window in the image. Okay, so given that we have maybe some black box algorithm that will do this proposing of regions for us, let's now think about how it is we could define a region-based CNN. So RCNN, which is one of the very famous, say relatively early on object detectors that certainly at least uses like region proposals, is named RCNN based on this name of region-based CNN. So how does this work? So what RCNN does is it takes some input image and it then describes using some given algorithm a set of regions of interest. So in this case, they constrain the numbers of regions of interest that they're gonna be considering to some fixed number, which is on the order of 2,000. So what they'll do is, so like the first step is they get the image, they pass it to this black box algorithm, which is not a neural network, and it will spit out 2,000 bounding boxes that are potentially containing an object that you would want to detect. At that point, what RCNN does is it actually crops out the image features, so the actual like RGB pixel features at each one of those regions of interest, and it then rescales them to be a fixed square shape. So every single one of these regions of interest, no matter what the original aspect ratio was or the original resolution, it'll either shrink down to 224 by 224 or upsample up to 224 by 224. And at that point then, those images are passed through some pre-trained convolutional neural network to extract features. So this convolutional neural network in RCNN was pre-trained on ImageNet. And at that point then, given the features that are extracted, it's going to have two final heads. The first head is going to try to predict a class for every single one of the extracted features corresponding to every single one of the regions of interest. And the second head is going to take the features that were extracted from the convolutional neural network and try to regress a bounding box. One distinction in what the bounding box that RCNN detects is it's actually defined as a transform. So what it does is it tries to correct for the region of interest bounding box as some translation in the horizontal and the vertical dimensions. So like the reason why we might want to do this bounding box regression is like kind of the first question is, do we need any bounding box prediction at all, right? Because if we have this region of interest algorithm, every time that it gave us some region of interest, it was giving us a bounding box. So in some sense, if we're predicting maybe that within this large bounding box on this example image, there's a human, why do we need to predict any, like we have the bounding box from the region of interest network. Well, it turns out that those black box heuristic algorithms are not perfect. So they'll produce regions of interest that could be improved. And so what RCNN tries to do is it tries to use this final bounding box regression head to improve the actual bounding boxes that were detected from the region of interest proposal network. And the way that it does that in terms of an implementation is by describing a transform. So it's trying to transform the bounding box from the ROI proposal algorithm as a transform into some better bounding box that's hopefully closer to the ground truth bounding box. The fact that this like trying to improve the region of interest from the proposal algorithm actually worked with a neural network was kind of indicative of future work, which we'll talk about in the next lecture, which actually tries to actually remove those black box algorithms entirely and just learn how to propose regions from just using a pure neural network. But okay, so what does this box regression actually look like at like a higher level of detail? So let's consider that we have some region proposed. So in this image of the cat, we have our region proposal with some center location px and py. So that's just like this blue point in the center of this image. And then also along with that, we had some predicted width of this region of interest, and then also some predicted height. What our model is going to do is try to predict a transform that actually changes this original bounding box. So hopefully making it kind of like fit tighter onto the object and also have a closer center, like a more correct center. And so the way that this output box at the very end of our overall detector is going to be defined is by taking the original predicted center and then transforming it as like a scaled version of the predicted width. So what we do is this Tx, which is learned from the model, is scaling the original predicted width of the bounding box and then adding that to the original center to predict the new bounding box center. You do the same thing then for the x and the y coordinate of the bounding box center that comes as output. But for the bounding box width and height that comes as output, what we do is we scale the original predicted width and predicted height by exponentiating some also learned tw and th. So the reason why we exponentiate is to force this scale factor, these two scale factors, to be greater than 0. So it can either expand if it's greater than 1, or it can constrain the original predicted width and height if this exponentiation is less than 1, less than 1, but still greater than 0. And then that bx, by, bw, and bh, this will be the final detection that's reported from the overall algorithm. But from the neural network standpoint, we're just trying to learn these 4 parameters here, or learn how to predict these 4 parameters. And so one reason why this specific definition that they that they use in RCNN has like a few nice properties. One of them is this fact that when the transform predicts all zeros for this tx, ty, tw, and th, your actual output, your final bounding box, is going to be the same as what the region of interest proposal algorithm gave you. So it's not going to change it at all. Question? So the question was, how does it know to extend the output bounding box beyond the region that it saw? So what it potentially can do, like if we go, let's see, so like this example is not a great example because well, I guess to some extent. So like if we think about what the convolutional neural network is going to get as input in this case, what it's going to do, right, what RCNN does is it will take the pixel coordinates that are within the blue box, and it'll constrain those down, it'll downsample them down to 224 by 224, and then feed that to the convolutional neural network. So it's possible that the convolutional neural network could actually identify that at this bottom edge, that it actually isn't seeing the sort of like a rounded bottom or tail of the cat. Like it's just seeing like this hard edge. And so potentially somewhere within that learned neural network, that might actually indicate that, oh, I need to extend the bounding box further down to actually like kind of encapsulate the entirety of the cat. So hopefully that's what the convolutional neural network would be like learning to detect in terms of features. And then the final regression head would hopefully be able to know when you've detected that the bottom portion of the cat isn't seen, how do you estimate sort of how much of an offset downward to extend the bounding box by? So that's kind of how, is like it has some visual knowledge of what might not be seen in the image just based on where this image chip that was cropped out ends. So I should clarify. So let me see. I don't know if I have so we haven't gotten to how this is trained yet. The loss for RCNN doesn't actually use the IOU. The IOU is a nice metric for us to interpret how good bounding boxes are, but it could be used as a loss function, but it's generally not, because if you have a predicted bounding box that has no intersection, then there is no loss, like there's no gradient information essentially. So instead what's used to train this, like this approach, is you actually know what the ground truth bounding box is. So you can actually, so because we know what the ground truth bounding box is, and we know what the region of interest proposal algorithm is giving us, you can actually calculate what the ground truth transform should be by just inverting essentially like these equations. And then we can use essentially just like some regression loss, like an L2 loss, to try to encourage the network to predict these exact transforms. Yeah. Okay, great questions. So one additional property of this algorithm, or of this specific definition of how you would predict a bounding box is nice, is that, so like I was saying, so when the transform predicts all zeros on how to scale the original proposal network's bounding box, the output bounding box is going to be the exact same as the region proposals, or the region of interest bounding box. And if we think about how that would tie in with some of the other training techniques we've talked about, if we were using L2 regularization in this portion of the network, L2 regularization is going to encourage all of the weights of the network to be near zero, and if all the weights of the network were near zero, you would actually have a transform of all zeros, because like if all of that final linear layer weights were zeros, then the final outputs would all be zero. So this is just kind of like a nice property. It's kind of saying, like, using L2 regularization with this definition of output for how you would predict a bounding box, it's sort of saying, like, it's kind of encouraging the network to default to the region of interest bounding box and only try to change the region of interest bounding box if it really is beneficial to your overall performance during training. So that's a nice intuitive property of this definition of bounding box transform. Another nice property of how we're predicting bounding boxes here is that we are scale and translation invariant. So what that means is that we're not giving our bounding box predictor network any information about where in the overall global image it's looking at, essentially, right? So we're just giving it the cropped, like we're giving the convolutional neural network the cropped image chip, and then that the features that are extracted from that cropped image chip are used to predict this transform. So nowhere does it know that a specific cropped image chip is looking like at the very top left corner of an image or the very bottom right. We're never giving it information that would allow it to make predictions based on where in the image it's viewing. And so that's another nice property of this. That would sort of ensure that our network doesn't overfit to where in the image it's looking. Okay, so now given this definition of just how the network would do a feed-forward pass, how can we actually train RCNN? So for training, in our data set, we're gonna have a set of images, and for every image, we'll have a set of ground truth bounding boxes. In addition to that, once we start running RCNN on this image, we're gonna have a set of proposed regions of interest for this given image. So there's another set of bounding boxes. So what RCNN will do during training is it'll classify these regions, these proposed regions into three different categories. You'll have positive regions of interest, negative regions of interest, and neutral regions of interest, as well as our original kind of ground truth bounding boxes just from the data set. So what are these three categories? So a positive region of interest is one in which there's a region of interest predicted that has an IOU greater than 0.5 with any one of the ground truth bounding boxes. A negative region of interest is one of the regions of interest that has an IOU less than 0.3 with all of the ground truth bounding boxes. And then a neutral region of interest is one that has some IOU between 0.3 and 0.5. So these thresholds, these IOU thresholds, these are hyperparameters that are set before training. And so this is one example then of like how the IOU is a useful metric. It's used a lot of the times as thresholding to try to decide during training or internally within the network, sort of like which regions we want to maybe use or not use, using a deterministic measure of overlap between bounding boxes. So in this case, this region of interest, which was originally predicted up here, is a negative region of interest just because it doesn't overlap at all with any of the ground truth bounding boxes, whereas these ones that are labeled blue or gray are either positive or neutral based on how much they intersected with the ground truth boxes. So, okay, so during training, so let's say we have our ground truth bounding boxes, we fed the image first through the region of interest algorithm, we got the regions of interest, we categorize them, now what do we do? So for all of the positive, let me think, let me go back one. Yeah, so for all of the positive regions, we're now gonna take the corresponding image chip for those positive regions, rescale it down to this fixed 224 by 224 size, and then feed it, each one of them independently through our convolutional neural network to extract features and then predict the final classification and bounding box for. So what that would look like is kind of illustrated on this slide. We have 4 separate positive regions of interest within this example. So each one of them gets fed through our feature extractor, and then once we have a feature for each of those, we once again feed it through like the classification head and then the box regression head to produce some class target and some bounding box target. And so at that point then, we could actually train based on some softmax loss for the classification that our model produces, and then some L2 raw loss or some like regression loss for the bounding box based on the ground truth bounding box, which we know we have, based on which of the ground truth boxes had an IOU greater than our threshold for this corresponding region of interest, which we did during the categorization step earlier. And so based on the fact that we have a ground truth bounding box, we can calculate those ground truth transforms since we also know what the bounding box for this region of interest was. So that then, those transforms that we can calculate will be our target, what we actually try to train the network to predict for the bounding box head. So very quickly, that's what RCNN will do during the training phase. During the testing phase then, once it's been trained, what RCNN will do is we'll take our image, which now we don't have any ground truth bounding boxes for. We'll first run it through our region of interest algorithm. We'll get a set of region proposal bounding boxes. And then for each one of these proposals, we're going to predict a classification score and also a set of bounding boxes. And that then would be the output from RCNN. So given this setup for how RCNN will work at test time, two problems that come up is, first, there can be a lot of cases where we have like overlapping bounding boxes, and so we'll look at an approach that we can use to try to sort of post-process fix the detections that come from RCNN. And a second problem, though, is how it is we're setting some of those thresholds that we used both during training, but now also at test time, right? Because at test time, if we're predicting a classification on all of the regions of interest, presumably some of the predictions that we have, like for example, if we have this region of interest in this upper right corner, might have a classification score that's hard, like that's kind of, it's just a number, right? Like it might be 0.1 confidence that this bounding box up in the upper right portion of the image corresponds to some non-background class. So somehow we're gonna have to pick a threshold of confidence, essentially, at which we would say detections from RCNN are actually considered objects versus if they're below some picked threshold, they're not gonna be considered objects. So let's think now about how we can try and go about solving these two problems. So on the first problem, this case of overlapping bounding boxes, let's look at an example of that. So the problem is that object detectors, and this is not just RCNN, this will extend to object detectors that we look at in future lectures. Object detectors can often output many overlapping detections that are very close to one another. So in this case, for example, like this is kind of just a handcrafted example, but this is very realistic of output that you'll see from a detector like RCNN. So you can see we actually have two instances of one of these Hershey's pretzel bags in this image. In fact, we might even have a three because there's sort of some occluded behind here. But within that, we have two of these instances, let's say, we have 4 bounding boxes that have been detected. 2 of them, like these 2 red bounding boxes, are very near to one another, so really kind of correspond to the same single Hershey's object in the foreground. And then these 2 bounding boxes, these blue bounding boxes in the back, are likely referring to the one Hershey's bag in the background of the image. So how could we try to maybe post-process these detections that we're getting from RCNN so that they don't have these duplicated detections? And the reason why we would want to get rid of or post-process away these duplicated detections is that, let's say that we were going to take these detections and then give them to our robot planner. We wouldn't want to tell our robot planner that there's 4 Hershey's bags in the scene, right? Because there's really only 2. We're just over-detecting the 2 that are in the scene. So for downstream tasks, we're going to want our detections to be more reliable. So an algorithm that's commonly used to handle this situation is what's called non-max or non-maximum suppression. And so what it's going to try to do is, as the name suggests, suppress any of the bounding boxes that are not sort of the maximum according to both confidence and IOU. So how will this work? So the steps of the algorithm are laid out in these numbered phases. So what you do is you take, for a given class, you're going to look at what's the highest scoring bounding box for this given class in this image, and you're going to sort of consider that one first. And in relation to that, what you'll do is you'll eliminate any of the lower scoring bounding boxes that have an IOU with that highest scoring box above some threshold, which you have to pick as a hyperparameter. So once you've eliminated then those lower scoring bounding boxes, you'll then just keep repeating this process. So you'll go back, you'll consider what's the next highest scoring bounding box, which I haven't eliminated, and then consider all of the lower scoring bounding boxes from that. Do they have an IOU above some threshold? And eliminate them if so, and so on. So let's step through and look at what this looks like. So in this case, our most confident bounding box is this one now that's highlighted in pink, this sort of light red color, that has a predicted score of 0.9. So that's the highest confidence out of these 4. And what non-max suppression is going to do now is compare pairwise what is the IOU between this bounding box and the 3 other bounding boxes corresponding to this class in this image. So the IOU between this light pink and then the kind of darker pink, or like the still light red bounding box, is 0.8. So that's above this threshold that we picked of 0.7. So what we're going to do then is, well, at the next step is we're going to eliminate this red bounding box from one of the detections, because we're going to say that that's actually a duplicated bounding box. So non-max suppression is going to suppress that detection. For the other 2, for the 2 blue bounding boxes, the IOU between the one that we're considering, this pink bounding box, this highest scored bounding box, and those 2 blues, is way below our IOU threshold of 0.7. So we're going to keep those 2 detections as to still be considered for non-maximum suppression and kind of move on to the next step of the algorithm. So at that point, we would have gone through steps 1 and 2, And now we've decided to eliminate this red, this like darker red bounding box. And now we're going to go back to step 1 to iterate through the process again. So at the next step of the algorithm, we'll take our next highest scoring bounding box, which is going to be this dark blue bounding box with a predicted score of 0.75. We're going to compare its intersection over union with all of the lower scoring bounding boxes, which is now just the 1 with a score of 0.7. And the IOU for those 2 blue bounding boxes, let's say, is very high, 0.85. So once again, that's above our threshold of 0.7. So we'll decide to eliminate that lower scoring bounding box once again. And at that point, we've gone through all of our bounding boxes for this image, all of our detections. We've performed non-maximum suppression. And now you can see we've reduced the number of detections down to just 2 correct detections. So those are the steps for implementing non-maximum suppression, which on project 3 we'll get a chance to do. Okay, so one issue though is that this kind of isn't the full story. Non-maximum suppression is very good at eliminating these duplicated detections, but it's not perfect. So if you have scenes that are very, very crowded with very similar objects, non-maximum suppression will likely fail to suppress all of the, all of the duplicated detections that your algorithms are probably producing. So this is still an open area actually of research in terms of how can we make our detectors better in these kind of cases. So there's actually work being done that's very active on trying to replace this handcrafted algorithm with a pure learned approach. So there's been a number of proposed approaches to do that. Right now, though, non-maximum suppression is still kind of the default that's used in a lot of these detection algorithms. So that's the one that we would recommend you implementing in practice. Okay, so let's say now that we've implemented RCNN, the forward pass, we've set up our training, we've set up now our inference with non-maximum suppression as like the final step at test time. The final question then is, how can we actually evaluate how well this object detector is performing? And so there is a metric that's used, this is the most common metric that's used on certainly all of the object detection data sets. It's called mean average precision, or MAP for short. Sometimes you'll also see like MAP, and then you'll see an @ sign with then like some number, like a decimal number. So you'll see like MAP at 0.5 or MAP at 0.75. So we should be asking, how is this metric actually defined? Because oftentimes that's how a lot of these algorithms are judged with respect to one another. So let's define it. So what mean average precision is doing is it's evaluating how well this object detector performs at test time. So what we're going to presumably do is we're going to run that object detector on all of the test images within our data set, and then try to evaluate how well were the detections corresponding with the ground truths. So for every single category within our test set, we're going to correspondingly predict a measure of what's called average precision that the detector was able to detect this one category at, and then we're going to average over all of these average precisions to produce the final mean average precision. Okay, so what is average precision? So average precision is what's called area under the precision versus recall curve. So let's look at how this is calculated. So let's consider what's shown here. So these blue boxes are going to correspond to, on one given image, all of, let's say, the confidences for different detections within this image for one class, which is the pretzel bag class. So these are sorted, these detections are sorted in decreasing confidence. So you can see like our first detection on this image was very confident of 0.99. The next one was still pretty confident with 0.95, and so on. And then these orange boxes represent the actual ground truth bounding boxes that existed within this image for the pretzel bag class. So you can see already we're detecting too many bounding boxes for this example image, this kind of hypothetical image. So to calculate the average precision for our model, given this test data set, this kind of one image test data set, how will we do it? So the first thing we're going to do is we're going to step through all of the detections and try to evaluate essentially at different thresholds what is our model's precision and what is our model's recall. And then that will be how we define the precision versus recall curve. So the way we do that is we're going to iterate through each of the detections in decreasing confidence, and we're going to check whether that corresponding detection had a match given some IOU threshold with one of the ground truth bounding boxes. So if a specific detection matches with the ground truth bounding box above our IOU threshold, we'll mark that detection as a positive case, and then we're going to correspondingly not consider this ground truth bounding box to be detectable again. So in other words, this metric is going to be incentivizing our models to only detect the ground truth bounding boxes one single time. At that point, if the IOU threshold for a given detection is less, or if the IOU for one of our detections with all of the ground truths is below some picked threshold, we'll mark that detection as a negative case. So that was like a false positive detection. And then we're going to keep going through all of our detections correspondingly. So once we've evaluated one of our detections with all of our ground truths and decided whether it's a positive or negative detection, we can then mark what the precision and recall for our model is given this threshold for confidence. So what that looks like is at this first level of confidence, which would be any detections above a confidence of 0.99. Yeah, so precision is true positive over true positive plus false positive. So that's 1/1. And then, yeah, so recall is true positive over true positive plus false negative. So that's 1/3, because so far we've only detected one of the three possible positive detections. So at that point, you'll mark this specific, at this specific confidence threshold, we have a precision value of 1 and a recall of 0.33. You'll then kind of iterate through this. So then you'll look at all of your predicted bounding boxes that are above the next lowest threshold. So in this case, because it's discretized, it's going to be like all of the bounding boxes above 0.95. So in this case, let's say that hypothetically this detection matches with another one of the ground truth bounding boxes in our data set above our IOU threshold. So we'll consider that as a positive detection. So then we'll update our precision and our recall, plot that specific point in our precision recall forming a curve, and you'll keep going through this. So you'll sort of step through at decreasing values of confidence. At every single one of those values of confidence, you'll get 1 point on the precision recall curve. And then at the very end, once you've gone through all of your examples, you can then measure what's the area below this curve if you imagined connecting all of these points on the precision recall curve that you actually measured. And so that area under this curve is what is called the average precision, and that just corresponds to one class. So this average precision just corresponds to the pretzel class in our data set. At that point, you would perform this same evaluation on our test images, but for the other categories in our detection data set, and then you would average them all together to get your final mean average precision. So your final mean average precision, let's just hypothetically say our data set had 3 classes, and each of the classes had an average precision shown here. Your mean average precision then is just the average of those average precisions. And so what that at 0.5 then corresponds to is the specific IOU threshold that we use to calculate this metric. So in this case, our IOU threshold, when we were comparing all of our detected boxes with the ground truth boxes, was 0.5. So we'd say that the mean average precision at 0.5 for this model was the value that we calculated, 0.75. Okay, that was going very fast through that, but that is the standard metric on all object detectors that's used. So next time what we're going to talk about is actually some more advanced, some more recent object detector models. So we'll talk about fast RCNN, faster RCNN, and then also a semantic segmentation model, mask RCNN. So after next week's lecture, you'll have all of the content you need to implement the faster RCNN model in Project 3. And with that, I'll stick around to answer any questions.